Hello everyone. Hope I am audible. Yes, fine. So, welcome to the first talk of this semester. As you can see, the title of the talk says "Far Beyond the Visible," where I wanted to convey the message that there is something which is beyond, which is visible to human eye, which human eye can able to perceive. But there are a lot of things which is beyond that, and for that we need science, we need technology to unravel all those stuffs. So. This will be the entire talk about. Basically, from the images and elements, you can see it's all about radio astronomy. So, radio astronomy is a field which is growing a lot in the in the past few years, has grown a lot in terms of developments, in terms of research, and is providing us promising results. As you saw, the recent discovery of nanohertz frequency gravitational wave background being detected by the pulsar tracking array, which had contribution from the Indian pulsar tracking array. That's why we are very much interested to know what is beyond, which is not visible. A lot of stuff, most like it's not just radio astronomy. You have gamma ray astronomy too, but it's like a larger part of the domain of astronomy and astrophysics after visible wavelength, you can say is what radio astronomy is, and there is a lot to see. So yeah. So this was a QR code of our website. Just if anyone wants to scan and check, meanwhile, you can do it. I recommend to scan it because the website has been published recently, as we explained. Yeah. So the search engine ranking might not be high enough. Like if you Google it, you might not find it. That's why I put up the QR code. After a few weeks, it should be improved again because our old website had a very good SEO. Yeah, hope you all have scanned, or else we'll see at the end of the talk. We can go next. So yeah, here people often misunderstand radio astronomy as something related to radio, which is not the case because you all have read about electromagnetic spectrum, the whole spectrum of energy. You have different frequencies. It has been defined at different frequencies and slash wavelengths, and you know about it. So similarly, as we can see in the visible range, we can see with our eyes. Telescopes can see at the wavelength of radio frequency, or the part of the frequency, the part of the electromagnetic spectrum which defines radio frequency can be observable, quite observable using various tools like antennas and telescopes, which we will be talking about shortly. Next. Yeah, so just a brief outline of the talk, what all things we will be going through in the entire duration of the talk is first, how radio waves are produced, basically. Next, a brief history of radio astronomy, how all things started, and how we grew up till the date at which we are. Next, we'll talk about radio telescopes. Next, the challenges and complexities involved in radio telescopes. The radio telescopes, different radio telescopes which are around the globe. I tried to list a few because there are a lot, but because of time constraint, all can't be discussed, or you can search it in internet easily. Then we have space-based telescope. Will I can just briefly tell you about it because I didn't get much images or information about it. Then we'll know about a phenomenal technique called radio interferometry, which has produced promising results in the current domain of radio astronomy. Then radio polarimetry, we'll also talk about it next. We'll talk about pulsars, fast radio burst, gamma ray burst. We'll talk about pulsar timing. About pulsar timing, there will be a complete talk by one of our professors, Dr. Roshan, and he will be explaining it in more detail. But I can give you a brief outline of it. Next, Einstein at Home. Einstein at Home is a citizen-based research kind of can be said as project, which you guys or anyone else who is interested in astronomy and astrophysics can explore. I will tell you about that next. And at last but not least, I will be telling about my experience at Raman Research Institute, where I worked last summer as a visiting student program. And yeah, starting with the cosmic radio waves. So, radio waves basically any electromagnetic spectrum is produced. Basically, electromagnetic spectrum consists of electric field and magnetic field. Electromagnetic wave. I mean. So, any electromagnetic wave can be produced when a charged particle accelerates. So, that's the basic line which you can consider that how radio waves are produced. And on that, things build up and it works like it works in a different way, and we obtain the radio waves from the cosmos. Yeah. So the first method is the most common. I have listed down three most common methods. There are different methods in which the cosmos emits radio waves, radio signals, but these are the three most common methods. First one is thermal emission. Thermal emission, people often misunderstand it as something which is hot, which has more energy, or which is having more temperature, will emit here radio waves. Will emit radiation. Yeah, it happens. It will emit radiation. But all of you know that Wien's displacement law, where it says that the temperature or the wavelength is wavelength of black body radiation is inversely proportional to the temperature. But here, if you understand it like thermal emission as in something which is radiated because of heat, then that electromagnetic wave will be of lower frequency because temperature is high. So this is not the case. So what happens is because of heat, because many astronomical, many celestial bodies, because of continuous undergoing of chemical processes and burning of fuel, they emit heat, they emit energy in terms of heat, and that leads to acceleration of particles, charged particles around it, in the gases around it, and in its atmosphere, which leads to production of these radio waves, as you can see the animation, where the particles are accelerating because of heat. Heat increases the energy of the particle and it accelerates, and you get EM electromagnetic wave. And depending on how fast or how slow it's accelerating, the frequency of the electromagnetic wave will vary. Next. Yeah. So you heard about now the thermal emissions. Now it's non-thermal or synchrotron emission. They are basically which doesn't involve heat energy. Heat energy from the celestial bodies. It doesn't depend whether the celestial body is producing heat or not. Because like let's say a star dies, and all the fuel in it is now over. Like it cannot burn more fuel. So gradually its temperature goes down. we cannot say that from those stars we cannot get radio waves. It's not possible. So it's now non-thermal and synchronous emissions are basically because of the strong magnetic fields of those stars, of those celestial bodies, which are causing the charged particles to accelerate, and that causes emission of radio waves. You can interrupt me anytime if you feel like asking something. Yeah. So wait, just a minute. So this is an image where I want to just point out, just keep it in mind. Maybe we can talk about it in the later slides. So that's the star, and the front one is a planet revolving around it. So what's happening is basically radio waves can occur from the star surface because the star also has some magnetic field. Also, the planet has its own magnetic field. So depending on how the gases are moving around both the bodies, depending on that, the particles will accelerate. As it comes across the magnetic field of the star, it will also accelerate. Also, if those same particles, those same electrons, if they come in the atmosphere or in the region of magnetic field of the planet, it will also accelerate, causing the production of radio waves or radio signals. And yeah, this is something quite which promises that radio waves are possibly a method which can help us to detect exoplanets around stars which are beyond solar system. Yeah, next. Yeah, finally, the third method is 21 centimeter emission, which is quite popular among young amateur radio astronomers because it's quite easy, I would say, to do research or to explore this region of radio emission. I will let you know why is it easy or why it carries less challenges compared to the other two. So 21 centimeter hydrogen emissions are basically because of neutral hydrogen. So this is a property of hydrogen in which it changes you know that there is only one electron revolving around the nucleus of hydrogen atom. So that electron changes its spin in a long period of time. It's not quite often. It's like maybe after hundreds and hundreds of years it will happen once. So whenever it changes its spin from, so these are the two states being displayed here, 1 and 0. So whenever it changes its spin, it emits energy in form of radio waves because the energy emitted has the frequency of 1420 megahertz, which corresponds to, if you calculate the corresponding wavelength, you will get 21 centimeter, and that is the electromagnetic wave which we are receiving here at Earth because of the flips. So now, how that if I say again that it's very rare, the flipping is very rare, then how is it easy? So because there are a lot of hydrogen atoms in the entire universe, it can't be quantifiable. So at least one hydrogen atom goes through this process, and you can get the 21 centimeter emission from everywhere in the universe. So basically, when you try to look at any part of the sky, you will see 21 centimeter emission. That's because of the cosmic microwave background, no doubt. But these things, the strength of these emissions will be maximum from the galactic plane. Whenever the galactic plane passes over our head, if we point the antenna, basically, we can get a strong signal from those regions because of a lot of stars and galaxies in that region. Yeah, next. Can you explain that graph? Yeah. So this is the 21 centimeter emission line. This is a 21 centimeter line popularly known, which is basically, so here its temperature. They have, like, the graph says its temperature, but it's, in general we say it as power level of the signal or the strength of the signal. They have calculated the corresponding temperature to that power level, and it's plotted across the frequency. You can see the frequency. So you can see there is a peak at around 1420.4. So this is 1420.6. If it's visible, right? So this is 1420.6. So it's the peak is around here. It's 1420.4. So why is it 1420.4? It's because of the redshift. So because of the redshift, which is causing the frequency to increase basically. So it's causing 1420 to lie in 1420.4 region. So we get a peak at 1420.4 megahertz. Mostly that peak remains same as of now since past maybe 100 years or something. So yeah, next.
I have a doubt.
Yeah.
What is the velocity mentioned in?
Where?
From zero.
Okay, that's okay, fine. Just to say, there is no plot here, but they wanted to plot it because this is the galactic plane you all can see. So we are trying to observe the galaxy rotation curve. So the velocity axis represents the velocities of different points of the galactic plane. But since there is no plot, so I don't think it has any significance here. It's just axis here mentioned. But the major information is about the power level at different frequencies, which we basically say power spectrum.
I also had a doubt. You just mentioned when spin flip happens, it releases radio waves. So that means that by spin flip, it is losing some energy from somewhere, and which is going out as radio waves. From where is it losing the energy?
Yeah, because of the spin, the electron is changing its spin.
But again, that energy of that electron must be quantized. So can there be some time when spin flip happens so many times that you can't flip it anymore because you have lost energy?
No. So the energy of the electron remains constant. It doesn't change it. The spin flip might happen anytime because electron has a spin, right? It might change. It might so changing means it will just flip its direction, right?
But it is releasing radio waves also, so means it is losing energy from somewhere. So where it is losing energy from?
The electron, right?
But if electron is losing energy, then how can you say that energy will remain constant?
So how can I explain it?
Then it might not be constant. Right?
No.
It might get disturbed after that.
No. Then it will cause instability of the atom. That cannot happen. So what he is trying to ask is from where the electron is losing energy. Because the electron has an energy state. So whenever it flips, the energy required for the electron to revolve around the nucleus remains the same. Talking in Bohr's atomic model in that regime. I don't want to go into quantum. So that remains same. But the electron, when it's flipped, when the spin of the electron changes, when its direction changes, it will release some energy from its own. Given that the energy of the electron revolving, the energy which is required for the electron to revolve around the nucleus remains stable. In that way. So
What do you mean
I
by
will.
its own? What is that energy? Is there any name?
As in, I'm unable to explain, but yeah, I can say like from its own, as in maybe I can come up with it later. Yeah, like I can formulate in a better way. So yeah, basically the energy is released because of the change of the spin of the electron. That is what causing the release of the 1420 megahertz radiation, and yeah, we can go ahead. I will come up with it shortly.
I think it's exactly when the spin of the proton and the spin of the electron are changed.
Yeah, they go opposite.
Yeah, so that interaction, the change in that interaction is what's causing the release in the extra energy. That's what you were asking. You were asking since
Where is that energy coming from which is releasing radio waves?
What you said is that since the energy is quantized, it can't keep losing energy, no? Otherwise,
Yeah.
you Rutherford problem. So the spins also interact, right? Now the proton has a spin and the electron has a spin. So their relative orientation with respect to each other has some self energy, has some interaction energy. When that spin is changing again, that change in interaction is probably causing the release in energy. This is like a vague explanation, even I am not sure exactly how many times this can happen. So even I had this question, but I think this will answer at least to a preliminary level. We can discuss this.
Yeah, we can look into it in the later part of the talk. Yeah, we can do this. So coming to a brief history, this image is of Carl Znansky, and this is the first antenna which detected radio signals from the universe. It's a turntable on which there are some few metal rods forming an array, and it's basically it was used for it was used in telephone industry to radiate signal as well as to receive signals from one place to another for communication purposes. But someday while just experimenting in general while experimenting with the antenna array system, they found some strange cosmic noises which are not from anywhere, and later why they confirmed it to be from the cosmos is they were finding the signal only once in every 23 hours 56 minutes. That's what one sidereal day is of Earth. I will come to what sidereal day is. But yeah, they were getting the signals once in every 23 hours and 56 minutes, and it was periodic. And they found that this cannot be some signal from the terrestrial, from any terrestrial place. It can only be possible if the signals are coming from the cosmos. Yeah, next. So this is how they earlier they used to do radio astronomy, because they didn't have digitizers, they didn't have computers to digitize the signal, because signals in nature they are analog, so we cannot really understand analog signals without getting them onto our computer screens. So what we need is a digitizer. But earlier days they didn't have digitizers.
Why we cannot understand analog signals?
Yes.
Why we cannot understand analog signals?
How will you understand analog signals? Like, how will you visualize first? It's not possible to visualize analog signals, right? Like, if you want to visualize a set of some information coming from somewhere, there are in analog form. So, let's say you are talking on your phone. So basically, that's the digital information which is coming from your phone's electronics into your speaker, and you are able to listen, as well as the words which you are speaking, they are also getting digitized. They are in digital form. No, your voice is analog. After getting into the phone, it's getting digital, and again it's getting analog and getting translated. So the intermediate phase you cannot understand. How will you decode what's there?
What's the problem in the understanding part of that?
No, like how will you visualize? You don't have that receptive, you cannot perceive that signal. That's what I'm saying. How will you perceive that signal? Okay. I hope I answered you. So yeah, this is how they used to do. They used to have one. You might have seen earthquake seismic wave detection machines. It's something very similar to that. The signal which come in analog form, they change, because those signals are basically voltage signals. They will change the reading in the voltage in the voltmeter, and that will lead to change the nib. It will displace the nib, and it will cause on a long sheet of paper the signals will get printed continuously with time. So this is how they used to it. This is the enlarged form of what they got. So this image I want to show you specifically because this is the spectrum of the first pulsar detection by Jocelyn Bell, who was a PhD student, and during her PhD in Glasgow University, she detected some unusual signals which were occurring periodically, and you can see those signals which are coming periodically. So, and also you can see a wave there. I'm not sure whether it's properly visible or not. Yeah. No, I cannot zoom. But yeah, there is a wave which is very similar to what you have seen in interference patterns. So it's causing because of interference of waves, because they used interferometry in those days to detect the signals. Interferometry has a lot of advantages. We'll come to interferometry and we can talk about it in more details. Yeah, next. So this is how the antenna array looked like in older days, where they used dipoles. Dipoles are basically a piece of wire can act as antenna. Basically, if you take even a steel hanger, keep it outside, just that the hanger's length or the element's length should be equal to equal to the wavelength of the incoming radiation, then only it can resonate with the resonance frequency of that element, that metal should be equal to the frequency of the incident radiation. Then only it can resonate, and then only you can get the signal through coax, basically, which are used as wires. So this is basically a phased array, older days phased array antenna systems. Those are basically just poles where you can see the wires hanging from one pole to another. Each wire acts like a dipole and a monopole basically, and if you just keep both the wires together, one end and the other end, the entire segment can be known as dipole. This is the dipole array which they used during those days for pulsar detection. This is the dipole array named as Gauri-Vidnur radio telescope. So Gauri-Vidnur is a place 100 kilometers from Bangalore, which has a very small radio observatory, where I also got an opportunity to work for a month. And I will tell about it in more detail. So this is the first page array they set it up during late, I guess it's late during 2001 or 2002, where they started, and now it's not that operational. Now they have better radio telescopes than these, and they are quite operational. So yeah, we can move ahead. So yeah, radio telescopes. Coming to radio telescopes, so radio telescope has made two major components. It's complex as well as you can say it's simple in terms of the elements in it, the components in it. Just talking about the telescopes, not the backend system. The telescope has a feed and something to guide the electromagnetic wave. So there you can see a dish, right? So this acts like a guide. Whenever some celestial electromagnetic, some radio waves are coming, they will reflect from the dish and they will reach the field. The field can be anywhere, maybe at the top of the antenna or maybe inside at the bottom. And there can be multiple reflectors as you want. And what contains inside the feed is a dipole. There you can see a dipole, animated version of dipole. This dipole is radiating, but something very similar happens when it comes to reception of radio waves, because they are not different. Radiation is the method they radiate is similar the method they receive. So here what's happening is when you apply alternating current to both the ends of the dipole, the electron oscillates from one end to other. That causes the acceleration of the electron causes formation of these waves, and they propagate as wave fronts gradually. Same thing happens when waves come to those dipoles. So to make the waves guide across something, a region, and reach the dipole, you need something, a solid structure which can guide that wave, the wave front, incoming wave front, and it can make it reach the dipole, and the dipole will then resonate, and then it will cause AC fluctuation, and you can receive the signal at your end. So these are the two main things which are required for an antenna to work properly. Then you have back-end systems, which back-end electronics, which are really necessary. But without these two, these two are the lives, the souls of antenna. Yeah. Coming before going more in detail about
what is the shape of that disk?
yeah, you can just go ahead. It's parabolic, but sometimes these days the latest antennas which they use are not parabolic. They are some weird shape where they don't use the entire surface of the parabola, the dish. They use some sections, and just to reduce the cost, the construction cost, the weight, and also it can withstand a lot of wind, and it can stay stable. But most of the time it's parabolic. There are something called phased array which doesn't use this antenna. I will show you how. So that's a phased array which you saw in the previous slide. Yeah, this is a phased array. Phased array basically directly the feed will be in the atmosphere, and the waves will the radio waves will come and interact with the feed. That will cause the production of the detection of signals. But to be more directional, suppose you just don't want to see some random direction, you want to see a particular direction in the sky. For that, you need a dish which will have high directionality. There is something called horn antenna, which also increases the directionality. I will show you how horn antenna looks like. That will also in few you can see something called feed horn there. In few dish antennas also you have the feed as a horn antenna. It's not simply a waveguide. So horn antennas has few components. While just remember how it looks like. While going there, I will let you know how horn antenna works and how it looks like. Yeah, you can go ahead. So sidereal time, before going more about telescopes, we have to understand what sidereal time is. So you know that Earth rotates around itself as well as revolves. So as it revolves, so one rotation is one day. So while rotating around itself, it's also changing its position with respect to sun. So this is the Earth. This is the line of sight. Let's say you consider the entire rotation to be one day. Now, as it rotates, it changes its position from here to here, which is 1 degree. So that 1 degree corresponds to 4 minutes. So basically, whenever you are rotating again back into the line of sight of Sun, it's 23 hours and 56 minutes and 4 seconds. That's what we call as one sidereal day. If we consider day to be 24, like the entire rotation of Earth with respect to the line of sight of Sun, we can call it as sidereal day. Now, solar day is I part. So this is the line of sight. If you keep this line of sight fixed, so whenever it rotates, when you come to this line of sight, there is nothing. You can see there is no sun because it has changed its position. 1 degree change in position. But again, to see the sun back, you need to rotate. You need to rotate around the axis to 1 degree. So that is what 4 minutes corresponds to. The entire rotation across this line, keeping in reference this line, is 23 hours and 56 minutes. But again, to see the sun back, you need a 1 degree or a 4 minutes rotation. So it's basically one day is 24 hours. We are rotating 4 minutes more every day because Earth is gradually changing its position with respect to the direct line of sight of Earth, right? So you know that what vernal equinox is, right?
So this 1 degree is convention or
No,
it happens?
yeah, it happens because the speed of Earth revolving around the Sun remains the same, right? It doesn't change. So as in 24 hours, it will sweep across the that particular line of around 1 degree. Yeah. So yeah, I was talking about vernal equinox. So anyone aware about vernal equinox?
You said speed will remain constant.
Yes.
You said speed remains constant.
Yeah, speed of Earth revolving around the Sun. Like I'm telling you, sorry, it's not the proper way of saying because the orbit is eclipsed. Yeah, the angle its sweeping remains the same. It's not the speed because the orbit is not circular, so you cannot say the speed remains constant. It's the angle swept by Earth. In every 24 hours, it rotates around itself. That remains same. So that is causing a 4 minutes difference. So vernal equinox, if you are not aware, just in brief, it happens twice in a year when sun is exactly at, depending on where you are situated. The sun comes over your head exactly at your meridian twice in a year, and it keep on oscillating from one side to other throughout the year. And the day on which you see the sun just above the meridian is not just above the equator, not like because you are not we are not situated at the equator. We are situated far from the equator. We consider our own meridian, but when it's exactly above the equator, we consider it to be the vernal equinox. So, in reference to that, the sidereal time is defined, and in reference to where you are situated, you have your own sidereal time, and that's what we say as local sidereal time. So, for every place, for every longitude in the globe, they will have different local sidereal time, and depending on that, it will change. So,
I have a doubt.
yeah.
So is vernal equinox like a direction or is it a date?
It's it's a day where like it's a date, yeah, basically, which we say it comes twice in a year in the entire 365 days. It comes twice when the sun is exactly above the equator, and because see you can see this you can see right the sun is in the line of sight of Earth, and we are considering that line to be a reference line to calculate the sidereal time. Yeah. So because of that, we need the sun to be exactly at above us to exactly pinpoint what is the current sidereal time, the local sidereal time is, and that will depend on where we are located, the longitude. Yes, I have a video. Okay. Doesn't have sound. So here you can see it's also revolving around sun, due to which exactly one sidereal day is 23 hours and 56 minutes. But exactly to look back to the sun, we need a 1 degree rotation. So this happens every day, right? So every day you have 4 degrees shift, like starting from the vernal equinox day, as it moves, you have a 4 degree shift, again 4 degree shift. So you cannot say that why there is no difference between, why there is not a 4 minutes difference between the current time and the local scientific time, because the vernal equinox has passed long back. That's why. Yeah, we can go. I got. Yes.
At the end of the video, there was some information about the leap year.
Yeah, it says that you shouldn't misunderstand it with the leap year. Sidereal time has nothing to do with the leap year. Leap year is needed because Earth takes, like it says, 365.24 days to. Leap year is basically, here we are considering the entire revolution of Earth around the Sun, and it in every 4 years it takes 365.24 days to orbit around the Sun, and that's what we call as leap year, and we have one extra day in the month of February. So it has nothing to do with, sorry, it has nothing to do with leap year, because we are concerned about it in a 24 hours span. In 24 hours span, what is happening, and the local sidereal time will be defined in that particular span, depending on where we are and how past or how in future we are from the vernal. Yes.
So is the leap year 365.24 sidereal days or solar days?
It's solar days. So coming to the first telescope project of India, the giant meter-wave radio telescope. It's situated at Narayangaon, Pune. It has 45-meter diameter dish. Around 30 such telescopes are spread across the village of Narayangaon in a Y-shaped array. I will let you know why is it Y-shaped, why is it not some random shape, because it matters a lot when you image something in the sky, known as aperture synthesis. The shape of the array matters a lot to do the interferometry and thus to produce the image of the sky. So that's why they are placed in a Y shape. This is the feed. This is a special feed of the antenna. So feed is basically, speed only stays one in general in any radio antenna dish. So here GMRT has 4 such feeds which are rotatable. So you can see the feed. This is the feed of GMRT. So it has a motor drive and it rotates as it's required, and they have 4 such feeds. So what are they? One is at 327 megahertz. Yeah, 332. Sorry, 332 megahertz speed. One is 1420 megahertz. This is the horn feed. Here we have 2 feeds, one at 510 and 200, and there is 100 megahertz speed. So depending on the frequency range they want to observe, the bandwidth they want to observe. Sorry?
Feeds. What are feeds?
So I explained it in the first slide, right? This is a feed. Feed is basically a piece of metal which acts like basically whenever a radio wavefront comes, electromagnetic wavefront comes, and it interacts with the metal, the electrons accelerate, and depending on the size of the feed, it will depend whether that wave will interact or not, and depending on that the electrons will accelerate and it will produce alternating current. This is a feed. This is how feeds look in general. So depending on the speciality and depending on our requirement, we change its length, we change its shape, we change its thickness. If we want a broad band, like 1420 megahertz, here whatever frequencies you are seeing, those are central frequencies. Central frequencies means you don't see just exactly at that frequency, you see a band of frequencies. That's the central frequency, and you have a bandwidth. Let's say if you want a 100 megahertz bandwidth, you will have 50 megahertz towards the left, towards the right, around 1420 megahertz. That's the central frequency. Next.
Is that one?
Yes.
Is that 45-meter diameter? Like the cross section is 45 meters?
Yes, 45 meters.
The largest telescope.
There are 30 of us. Yeah, it's operated by NCRL. They have the entire NCRL as well as TIFR. So the second telescope, which is a gigantic project, is Arecibo, it's located at Puerto Rico, and recently, not recently, few years back, it collapsed because of, you can see the telescope is basically, they don't have a dish. They use the piece of land itself to make a dish out of it. They just have their feed. So the feed is the topmost point, which is suspended via cables, and those cables are attached to the mountains around it. So that place is itself curved, and just with a few, what we say, we use some reflectors in case of radio astronomy, just to increase the sensitivity of the telescope. We do not use directly the piece of land, because that the piece of land cannot reflect much. We use some metal, some sheets to make it more reflective, and that's why they have made some modifications. And the rest of the technology is used in making the feed and the suspensions which you can see. So one of those suspension cable broke, and which led to collapsing of the entire feed, and it broke the entire dish as well. So it happened few years back. I don't remember when. Yeah. So yeah, this is how the just a brief view of how the telescope looks like. This is the primary reflector, which you can see on ground, and the feed has a dome shaped object which carries two more reflectors. So this is a secondary reflector. This is a tertiary reflector, and actual feed is exactly here. This is the focal point. Also, again, whenever I say feed, just see that image of the small piece of rod radiating or receiving radio waves, right? So here the feed is located. There are few more reflectors to be more directional, to increase the sensitivity of the telescope. Yeah. Next. Yeah.
So what was the need of such a large dish?
Okay. So you guys have read about resolution of just about resolutions in optical physics, right? So resolutions are basically dependent on the wavelength of the electromagnetic wave at which you are seeing. So radio waves have a larger wavelength. So how the resolution is dependent on wavelength? Those are inversely proportional, right? It's 1.22 lambda by d. So those are inversely related, and that's why to see a larger wavelength, we need a larger aperture, exactly to receive that wavelength. So that's one of the major challenge which I can say about radio astronomy. It needs a larger piece of land to set up telescopes, because the wavelength itself is large, and to be highly sensitive, to have a better resolution at that particular wavelength, you need a larger area, you need a larger dish as well. So that's why when he asked why not why the size of the dish is 45 meters here, still they wanted to increase the size. So they cannot increase the site beyond that limit, because there are a lot of constraints of the land. So what they do is they use multiple dishes together in a span of land. Apart from using a single large dish, they use smaller dishes at a big piece of land, distributed at some particular shape, and that acts like one entire dish. So that's why we call it aperture synthesis. So, whenever the Earth rotates, the position of the disk changes with respect to the galactic source, the radio source which we want to observe, and as it rotates, the entire thing. So, this is So these are the positions of the radio antennas of the radio telescopes. This is how GMRT looks like. There are 30 such, 45 meters each, and as it rotates, as the earth rotates, this thing also rotates with respect to the source which we want to observe, and these also change their positions. The center one remains constant depending on where is it located. Just if I talk about let's say GMRT, it also revolves because we can say that the position is not like such that the entire thing rotates and the center remains constant. So it sweeps gradually with time, all the points sweep, and in the entire day it will be one aperture, which can be after some post processing techniques can be synthesized, and those informations can be decoded, and you can obtain the entire image of the sky or the source picture that you look at. Yeah. Coming to the third radio telescope array, it's Murchison Wide Field Array, which is located at Australia. So they have used it. So basically, this particular array is used for low frequency observations, and it operates from a frequency range of 70 to 300 megahertz, as you can see. And the main aim of this array is to observe 21 centimeter emission, as I said, as well as to observe the epoch of reionization, the cosmic microwave background, to study the Earth's ionosphere, right? These are kind of these antennas are, if you want to understand why they are shaped like this, these are called bow tie antennas, where these two act like one dipole. If you see the top view of it, this acts like one dipole and this acts like one dipole. So they receive two different polarization of the radio waves. So we'll talk about it when we will talk about polarimetry, because you have polarization in one direction. Let's say if you have polarization in this direction, this set of dipole will receive the signal. And if you have polarization in this direction, this set of dipole will receive the signal. As well as again the same thing happens as the earth rotates, it also rotates gradually like this, and depending on the incoming incoming wave polarization, it will act differently. So this is how it works, and from the bottom of these you have coax cables. Coax cables are basically the kind of nerves in radio astronomy where signals are used to transmit, and you get the signals at your end, at the laboratory end, and you can do the post processing. Yeah, next. Yeah, square kilometer. So square kilometer array is the future project, which will be the world's. It's an international collaboration of different countries, and it will be after its construction, it will be the world's largest radio telescope array, and they will work simultaneously. One more thing I wanted to say you, just outreach. Murchison wide field array, the backend system has been developed by India. So the Australian Astronomy Corporation, they gave it to India, and it was done back 10 years ago, I guess. And it was done at RRI in the Digital Signal Processing Lab. And what they decided to give the technology back to them after working on it, and they decided to keep few antennas here back at India so that it can be used as a purpose of student research. So they gave back all these sets, and they kept only 8 of those. This is one type. So this is one array. So they kept 8 tiles of those, and the project they named it as SWAN, which is Skywatch Array Network. It was started by Dr. Avinash Deshpande, who is retired professor. Now he's at IIT Kanpur, and 8 of those tiles are already sent to different places in India. As far as I remember, IISER Mohali, IIT Indore, IISER Pune, IIT Roorkee, IIT Madras, like those eight institute have those. Along with that, one tile is situated at RRI, not at RRI, it's at the observatory which I said, Gaurav Radio Observatory, and those will work simultaneously as a network of telescopes, network of radio arrays, and they will give results in near future. So how they will work simultaneously is a little bit more about it. They work with the help of GPS. So these array, every tile has one backend system. So let's say you have one tile at, let's say this is Bhopal, one tile at let's say Mohali, and one tile let's say Madras. Right. So you have a radio source. All the three are receiving signals from the radio source, but they will receive those signals at different times because they are located far away. So they need to be connected in such a way that even if they receive the signal at different times, the computer records those signals at that particular time, the time at which we want the signal to be. And that will help us to create a interferometry mode observation, and that will help us to make it function like a very long baseline interferometry.
What do you mean by interferometry?
I will talk about it. So in later, we'll talk about it. If I talk now, it will be a longer. It will waste a lot of time. So making the arrays to be located at different places and connecting it with the help of GPS. So GPS is basically whenever a satellite crosses, the GPS satellite crosses, it will send a pulse. Those pulse will be received by all the three arrays simultaneously. And whenever they receive one pulse, that is one tick. So GPS is basically used as a clock here. We do not use the clock, the computer clock, or any other kind of clock. We use GPS as a clock, and every time there is one pulse from GPS, all the arrays located at different locations across the subcontinent will record the signal simultaneously. Right. So basically that will add some delays as well. The electronics has few components which will add delays to the incoming signal. So let's say the signal received at Madras is at 11:56, and here at Bhopal we are receiving the signals 4 minutes later at 12 AM or PM, doesn't matter. So just to keep both the recordings simultaneous, both the reception simultaneous, we'll add a 4 minutes delay at the Madras end, so that all the signals will be like these two places will receive the signals exactly at 12. They are receiving the signal, no doubt, at these times, but electronically from backend will add some delays so that they will be recorded at the same time. Right. So yeah, I hope it's kind of we can go ahead. Yeah, I was talking about square kilometer array, which will be a huge project in near future. It has two different parts. One is square kilometer array low and mid. Low is operational in a low frequency range, which is 50 to 350 megahertz, and mid frequency range is around 350 megahertz to 15.4 gigahertz, which is quite a large frequency bandwidth, and it will be complete maybe by 2027, I guess. I'm not sure, but it will be the world's largest as well as longest baseline radio telescope.
So baseline is the different.
Baseline is the length between two different arrays located in different areas. So the distance between Madras and Bhopal will be the length of the baseline. That is one baseline.
Why such a huge difference?
So that is the whole point, right? Instead of using a very huge disk, we'll use telescopes at longer distances, and then
I'm asking between these two, lower and higher.
why there is a
Huge difference. There is a difference of like almost 85 kilometers.
difference in
Between scar low and scar.
yeah difference in what?
Baselines.
Oh, baseline length. So this is the maximum baseline length of low, because that's what they need to operate at that frequency. It's enough for them. But for SK mid frequency range, they need a longer baseline, which is around 150 kilometers. Like in between two set of antenna arrays, there will be a distance of 150 kilometers, and there are such 197 dishes.
Why its maximum is right? Is it something like it cannot be more than that?
If yeah, it's something like that, because again it comes to resolution, again it comes to sensitivity of the entire array when it functions together. If the baseline length is more or less than that, this is the optimal length which they found, that it will lead to maximum sensitivity and maximum resolution of whatever we are observing. Yeah. Oh, sorry. So I guess some blank slide came. So yeah, going ahead with pulsars, fast radio burst, and gamma ray burst. So we'll talk about them in brief, because we really don't have much time. So coming to pulsars, yeah. Pulsars are nothing but very fast rotating neutron stars. Again, talking about neutron stars are stars after their death, they collapse and start rotating at a faster rate, because of as they collapse, the rate of rotation increases, and once the fuel get over, there is no more burning of fuel, there is no more energy, so it keeps on rotating the neutron as a neutron star. So yeah, now how these radio beams are produced in the figure which you can see. So as the neutron star rotates, the atmosphere of neutron star contains a lot of charged particles, gases, which come across the magnetic field of that neutron star, and it accelerates, causing production of radio beams. And those acts like as if you are in line of sight of that pulsar, and the radio beam is coming towards you, you will get a pulse at every particular time. Like at every particular instance of time, you will get one pulse, because that acts like a lighthouse. As you have seen lighthouse, if there is a person on a boat and is at sea, and this is the shore, and there is a lighthouse, the light keeps on rotating, and every time the light comes in line of sight of that person, he sees a bright flash in their eyes, and that's what similarly happened, and that's why we call it as celestial lighthouse. Whenever we come in the line of sight of those beams, exactly, we see a flash. We do not see, because we are not capable of looking. We are not capable of perceiving radio waves. That's what antennas see, and they see a surge in the power level as the pulse comes in line of sight of those antennas. So the first pulsar was detected by Jocelyn Bell, which you have seen in that plot. There are few pulses across. Those pulses are not that clear. The reason is because older days the telescopes were not that sensitive, and the latest telescopes which uses better electronics and better digitizers, you can see better quality of the data, and the pulses are quite prominent. So Pulsars also they also lie in the region of optical as well as X-ray, but most of the pulsars are in the radio region.
I have a doubt.
Yeah.
So, are the radio beams rotating like this?
Yeah.
So, they are not present on the poles.
They are located at the poles. Yeah.
But then, how are they like rotating like this if they are present on the poles?
Sorry, didn't have.
If
Magnetic pole, right? So this is the pole. This is the axis. Let's say this is the what they have. Okay, the rotation axis. Let's say here in that figure they have considered this to be rotation axis, and this is the let's say magnetic pole. Here the strength at poles, the strength of magnetic field is maximum, and whenever the particles, the charged particle come towards this region, they get accelerated at quite a high speed, which causes a beam to be produced at this as well as at this end. So let's say you are an observer here at Earth, and whenever if the beams are in your line of sight, then only you can see the pulse. Otherwise, it's quite difficult to actually. Maybe you will get some signals, but they cannot be periodic. Let's say if one beam is in your line of sight and the other is not, then you cannot really confirm whether that's a pulsar or some unknown radio frequency. It's difficult to confirm. So they should be in your line of sight, and that helps you in detecting them. Yeah. So this is something similar to what is there in the optical domain. We call it HR diagram, Hertzsprung-Russell diagram. It says that in the entire lifetime how the star moves from one stage to another, and how its temperature, how its energy, luminosity changes. So this is the change. This plot shows the period. Period is the period of rotation and the period derivative. Okay. So they have found that most of the stars, most of the pulsars are located at this particular region, and very few pulsars. So these pink triangles are in X-ray and gamma ray regime, whereas most of the radio pulsars are at around this region with period to be 1 second and period derivative to be in order of 10 to the minus 14.
What is period derivative?
The derivative, time derivative of the period.
Why are we plotting a graph, such a graph?
The need is to understand more about the life of the pulsar and the stability of the pulsar. So they have, I am not sure about the exact mathematical expression which defines the stability of the pulsar. I have to read more about it. But the stability of the pulsar is dependent on the period derivative of the pulsar. If not, it's not explicitly dependent. It's somehow dependent on the period derivative of the pulsar, which determines whether that pulsar will exist for a longer period of time in the universe or not. And we are plotting it across the period. We are locating the pulsar across the period as well as period derivative, and we are finding that most of the radio pulsars reside at this particular region of period of around 0.1 to 1 second. And this line which you can see below this line, there is no pulsar, like apart from 4 or 5 you don't see. So that's what we call our death valley, because we haven't find any pulsar at this particular region as of now. So they call it as death valley in the advance.
What's the unit is ERG per second?
Sorry? Yes. Energy. Yeah, they don't just to indicate at that period what energy corresponds to roughly. They have just mentioned it in the plot just to indicate that most of the pulsars at this particular period range, they have this much energy, and that energy is a function of time, as you can see, per second. Yeah, you can go ahead. Again, coming to fast radio bursts, they are basically magnetars. Magnetars are nothing but pulsars or neutron stars which have a very strong magnetic field, even stronger than pulsars. Their magnetic field is thousands to 10,000 times stronger than magnetic field of Earth, and they emit some flares, right? So every star, while expenditure of fuel, they emit some radiations, they emit some gases from their surface, and like those, they emit some flares, and those flares, when they interact with the magnetic field, they somehow collide between themselves as they radiate outside. They accelerate, they radiate, and they collide between themselves. While colliding, the acceleration of those charged particle of those electrons increases further, and the region where they collide, let's say that this is the region where two collision happens. This is the first flare which went. This is the next flare which is incoming, and they collide. And in between the collision, there are X-rays easily, but the higher frequency electromagnetic waves. But the lower frequency electromagnetic waves, because of lesser energy, they gradually sweep out of the region where the collision occurs, and the X-ray, as they gradually get redshifted, they also get into the radio domain. So this is what basically a fast radio burst looks like, and these FRBs are quite rare. You can say they happen in once in a year, or maybe once in 2 years, and they are very difficult to detect because magnetars are itself rare, and there are they are magnetars are itself rare. That's why it's difficult to even find FRBs. So going ahead, we have few FRBs here, which you can see. So whenever there is a burst in those magnetars, there is an influx of radio waves, and that when reflected on Earth, we see a sudden change in the flux energy. Here you can see at different times you have a rise in the flux in the energy level. These are the 2D plots which show those energy levels at different times and at different frequency ranges. So FRBs are quite broad in nature. You can see the frequency ranges from here, let's say from 1200 megahertz, well less than 1200 megahertz to around 1500 megahertz. So it's quite range. You have signal in entire region of frequency and at this particular time. Right. So they are quite energetic and quite they prolong for a longer time, and they're prolonged, and these are the these are the six FRBs detected as of now by different telescope arrays. So you can see FRB 8. So this number represents the identification, which is basically the date, month, and year of detection. So this is the year. This is 2018 January 10th. So year, month, and date, they are written as such because they are quite rare and it's difficult to detect. So they identify them in terms of the date of detection. So now you can again ask that why, then how, if the same thing is happening, right? There is a sudden flux of energy. You can see a spike in FRBs as well as in pulsars also. There is a sudden flux of energy. How they are different? Yeah, you can see from this plot, which is rate the period of rotation across the energy, the isotropic energy of the pulses which you get. You can see it's quite periodic. the rate changes linearly. But in case of FRBs, it's not linear. As the time, like as you grow through the time, it's not linear. It changes in a, let's say this is quadratic. This can be said as not linear, and this is how they are different. It's not that pulsars are basically the pulses which you receive are quite periodic. They are quite accurate in terms of the incoming pulses. But FRBs are, they, you see a pulse which remains for a longer period of time, and with time it vanishes. The energy limit goes down. So that's how basically they are different from each other. Now, yeah, this is animation. It shows this is in optical region. No, sorry, it's in radio only. It's a radio image of the sorry, it's GRB, right? So I pardon, I forgot to mention the title. So these are GRBs. Gamma ray bursts are even quite energetic than FRBs, where some galaxies, very few. We don't have much gamma ray bursts as well. There are galaxies which, due to their, again due because of their magnetic field and the interaction of the gases, the gas clouds around it, they accelerate, and that causes a rapid influx, a high influx of radio waves at Earth, and you can see the sudden change in the flux. Okay. So in that region, in the image you can see that's a radio image, and that shows how it changes with time. This is one more image of GRB. Again, sequence GRBs are also, the nomenclature also remains the same for GRBs. The year, the month, the day. The first one is in optical region. You can see a light flashing. That's a gamma ray burst which is occurring because it's a GIF. It's repeating like periodically, but it happens once and it stays for a longer time and it vanishes. Here, what is happening is these are X-ray rings because of presence of gamma ray, because of the gamma ray burst. It's not clean. No. It's not. It's an animation basically where you can see this ring here. It expands with time because of the presence of GRB. Because of occurrence of the GRB, the ring expands, and that ring we can see in the X-ray dome. When we use a telescope which can operate at the frequency of X-ray, we can see a ring expanding across that particular point where the GRB event has occurred. Yeah. Now coming to interferometry, interferometry is nothing but a special technique which are used for imaging, for aperture synthesis. They use the phenomenon of interference, which you all have read in your classical physics. And whenever there is a path difference between two incoming electromagnetic waves, they interfere they interfere among themselves, and they cause fringes. They cause a fringe pattern to occur. And using this technique, we we can go ahead and see other images. Yeah. So using this technique, we can do a lot of things. Mostly, it's used for the purpose of imaging, and this is the baseline length, as many of you, as you were asking. So this is the baseline length between two radio antennas, and because of this length, there is a difference in reception of the signal from the source, and because of that, and there is a path difference between the reception. Right. So here the signal comes at a later point of time compared to this. So here the signal has to travel extra distance to reach the field of this telescope compared to this, and because of that there is an interference pattern. So what we do is we use certain statistical tools such as correlation, and we calculate correlation coefficients, and those help us in imaging the sky with the help of the information which we gather from these signals. So these are the basic methods which are used in interferometry. Starting from like there should be a baseline, right? So there should be a distance, significant amount of distance between two telescopes. Then the signals after they are received, they need to be combined together, right? Then you use some statistical tools, and finally after using that, after doing some maths, I don't want to go that deep into the maths because we don't have much time. We can talk about it later. Using that we image the sky. Now coming to polarimetry, I hope you are clear what interferometry is. More or less. Coming to polarimetry or polarimeter is a device. Polarimetry is a technique. Polarimeter is used to so when I talk about dipole, so you have seen dipole is just this. So this is along one axis. So whenever there is electromagnetic wave, let's say we are talking about radio wave. So whenever there is a radio wave coming at this polarization, it will just go through it. It won't get detected because it's not the polarization is not along the dipole, the direction dipole is placed. So only the electromagnetic, the radio waves which are polarized across this direction, parallel to the field, those will get detected by the field and will get signal from them. So basically, it can be said like we are losing half of the signal or half of the information which are coming from different radio sources, and because of just one dipole, and which is placed at a particular direction, we are losing half the information which could have been beneficial for a lot of different purposes. Let's say to understand the strength of the magnetic field of the star or the direction of the magnetic field of the star, because radio waves, again, as I said, basically they are produced because of acceleration of the charged particle, and the direction of the magnetic field will depend the direction of the charged particle accelerating. That will depend on the polarization of the radio waves which are getting emitted from that. Yeah. So you will read. You have major topics this semester. Yeah. So we'll read about Stokes parameter where you will be knowing more about the I, Q, U, and V parameter. So I is the total intensity, the both polarizations combined. Q and U, they are linear polarization, and V is the circular polarization parameter. These parameters are necessary to compute or to understand the entire energy or the entire intensity of the incoming radio waves. So here you can see how magnetic field, the direction of magnetic field is determined using polarimeter. So if the direction of magnetic field is this, the electron is getting accelerated in this direction, the electric field will be in this direction and the magnetic field will be in this direction. It's not properly imaged, but you can visualize. So as it goes through the interstellar medium, it will rotate because it's interacting with lot of things. So firstly, it can help us to nearly predict the direction of the magnetic field, the strength of the magnetic field of the source from which it is coming. Second, as it passes through the interstellar medium, this is basically the interstellar medium, because of rotation of the electric field and the magnetic field, it can also tell us a lot of informations about the interstellar medium, the properties, the composition of the interstellar medium at R. So that's the importance of polarimetry, and that's the importance of understanding both the polarization of the radio waves. Good. Next. We'll cover it a little faster. I don't think how much time do we have?
It's 10, 20.
10-20 minutes. Okay. Yeah. So Einstein at Home is a project where what they do basically is, so you guys have computers. So to process data, you need a system, and the projects which they do, they will use your computer time to analyze the data. You don't have to do anything. You just have to install few sets of softwares, and you just have to contribute your computer time. It doesn't require any other contribution from you. It's a basic citizen science project, and it's been like around 5 to 10 years they are operating this. Multiple organizations, Max Planck, Gravitational Waves Institute, Max Planck Institute of Radio Astronomy, all are operating this project, and they will just use your computer time for what purposes? One is for gravitational wave detection using LIGO data, and they will use LIGO data. Meerkat is another radio telescope which is situated in South Africa, as far as I know, and they use their data as well as some gamma ray telescopes, and they use your computer idle time to process the data. It will happen in the back end of your computer.
So what is idle time?
Just the computer time. It will take your processor and it will process the data in the background. It won't affect any of the things happening in the computer. Just that it will use some performance. It will reduce the performance of computer for that particular time. That can be controllable. You can set whether you want to allow your computer to process the data or not. This is their website. You have to just install, I guess, few softwares. There is a BOIMC manager where you get project request and you can accept the project whether or not you are available at that time or not, and depending on what you want, depending on whether you want the data to be processed or not. So,
Which kind of data is this process?
as I said, it's the data from LIGO, gravitational wave detection, and data from Meerkat. Meerkat is another radio telescope array, as well as a gamma ray telescope, Fermi gamma ray telescope, and some archival data which they have. Just they need the computer time of yours, and they will be processing the data. And if they find something new in the processing, you will be given a certificate as your computer is being used and they discovered the data using your system idle time. So just outreach of the project. So going ahead with pulsar timing experiments. Pulsar timings are basically you observe the time of arrival of pulses from different pulsars across the sky, and you keep on recording them for different purposes. Might be you can use them as clocks because they are very accurate. You can use them for detection of gravitational waves, which is the main thing which people are concerned about, because you see, because in radio astronomy we use a large area because radio waves have a longer wavelength. Now imagine how long the wavelength of gravitational wave would be. Gravitational waves which are from the black holes. The black holes are quite massive, and as they rotate, the period of rotation of black hole is quite low compared to the period of rotation of the neutron star, or even when two neutron stars are merging together. The period of rotation is quite slow, so quite fast compared to the period of rotation of two black hole mergers, let's say, because they are massive. And because of that, the the waves which are produced in the space-time domain are quite of a longer wavelength. I cannot discuss more about gravitational waves. We can have a talk about it in a later period of our semester maybe. But if they are basically ripples in the space-time, which have quite long wavelengths. The wavelengths are in order of kilometers. So you need a quite longer baseline, and the only way possible are pulsars. Pulsars are kilometers and kilometers away from us, and the distance between two pulsars are also very low. So using that advantage of their long distance, you can use them to probe those gravitational waves. So yeah, this is what they are trying to explain. Whenever as I said, pulsar, the time of arrival of every pulse is quite accurate, and you can predict all the time of arrivals of pulse if you know the correct time of arrival. You can predict all the time of arrivals which will be coming ahead. But whenever you find some anomaly, whenever you find a slight difference in the time of arrival, there can be some change or some interference in between which have caused that. And in the later studies, a lot of things can be inferred from that. And this is how they have understood the presence of gravitational wave background. Because what gravitational waves do is they contract and expand the space and time. So if this is space, this is a space in 3 dimensions. This is space time. So just to represent in 2D. So what gravitational waves do is if this is the object, they will expand it in this direction one and contract it in this direction. So they do this and this. So one is plus polarization, one is cross polarization. This is how they define it. This one they call it as plus, and this the other way they call it as cross. Whenever it happens like this, the contraction is happening in this direction and the expansion in this direction. Whenever it turns, it happens in a cross manner. So they have two polarizations here. They don't have something in optical or the radio domain, which we say as linear and circular. They have cross and plus. Maybe you can understand it in a better way when we have the talk by Dr. Mehresh. And he will be discussing about it in more detail. Pulsar timing array, as I said, they are used to detect gravitational waves which are caused by merging of supermassive black holes, because they are quite massive, and the gravitational waves produced from the mergers are quite of a lower frequency and a larger wavelength. But when it comes to gravitational waves from binary stars, supernovas, or even pulsars, they are of quite high frequency because the rate of rotation is quite high. They are comparatively of smaller mass, and the energy of the gravitational waves produced here are of quite high, and the frequency is quite high as well as the wavelength is quite low. So because of lower wavelength, we can have a lesser piece of area, and we can easily detect them. And for that, we use ground-based detectors, which are nothing but LIGO. Those are of few kilometer scales. And here, pulsar timing arrays, they are of galactic scale, like around hundreds of kilometers to thousands of kilometers scale. So this is the recent discovery where they detected the gravitational wave background. This is something called Helens and Downs curve, where they used what they did basically was they correlated the difference between the time of arrival and the actual time of the pulsar incoming pulse, the pulsars, and they plotted it across the difference, the angular difference between two pulsars, and they found this model. This is a theoretical model. The black line which you are seeing is a theoretical model, and the dots are the actual data being plotted, and it's found that it quite follows through the same line, and this is what they can. This line which you can see is because there is no gravity. If there is no gravitational wave background, you will have a straight line passing through zero, because the time of arrival of pulsar subtracted by the actual time of arrival will be same, so it's zero basically. So if you correlate the time of arrivals of different pulsars, the final result will be itself zero. So the line is passing through zero. But because of different pulsars and different time of arrivals and different differences in time of arrivals, which we term it as time residuals, we see this plot, which is modeled theoretically, and after getting the data and after plotting them, we find to be quite a similar and follows the same pattern.